Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really intriguing paper about boosting reasoning in large language models, or LLMs, using something called self-backtracking. It's a pretty hot topic, so I'm excited to hear what everyone thinks.
Yeah, I've been following this closely. This whole area of improving LM reasoning is critical. I think self-backtracking is a clever approach, especially when we consider the limitations that have been popping up with just scaling up models.
I'm a little more skeptical, I have to admit. If self-backtracking sounds interesting on the surface, but I worry that it's just another layer of complexity on top of a system that fundamentally doesn't understand anything. Is it really a step towards AGI, or just a clever hack?
That's a fair point. My concern is less about understanding in a philosophical sense, and more about whether these models can actually represent and reason about the world in a meaningful way. I suspect self-backtracking could potentially address some limitations. Deep learning feels so brute force in many ways.
Okay, so before we get too deep into our opinions, maybe we should level set and talk about what self-backtracking actually is. In essence, it's a mechanism that allows an LLM to retrace its steps when it encounters an error or inconsistency in its reasoning process.
Exactly. Think of it like a debugger for AI. When a program encounters a bug, you can step back, examine the code, and figure out where things went wrong. Self-backtracking does something similar for LLMs. It allows the model to go back and reevaluate its previous decisions, identify the source of the error, and try a different path.
So, it's essentially adding an undo function to an LM's reasoning process? That makes sense, but I still wonder if it addresses the core problem. If the initial reasoning is flawed due to a lack of genuine understanding, won't the backtracking just lead to a different, equally flawed conclusion?
I see what you mean. The effectiveness of self-backtracking probably depends on the nature of the error. If it's a simple mistake in applying a rule or retrieving information, then backtracking might be enough. But if the error stems from a fundamental misunderstanding of the problem, then it might not help much.
Yeah, I think there are different levels of errors. Consider a simple example. The LLM is asked if John is taller than Mary, and Mary is taller than Peter. Who is the tallest? A basic LM might get this right most of the time. But if you throw in some irrelevant information, like John likes apples, it might get confused. Self-backtracking could help it filter out the noise and focus on the relevant information to arrive at the correct answer.
Right, and that filtering aspect is key. Self-backtracking isn't just about fixing errors, it's about improving the efficiency of reasoning. By retracing its steps and identifying the critical pieces of information, the LLM can learn to avoid similar mistakes in the future. This fits well with a data-driven approach to improvement.
But even in that simple example, the LLM isn't actually understanding the concept of taller than. It's just recognizing a pattern in the data. Self-backtracking might help it avoid getting tripped up by irrelevant information, but it doesn't address the lack of true comprehension. A neuro-symbolic algorithm, on the other hand, could explicitly represent the taller than relationship as a symbolic rule, which would allow it to reason about it in a more robust and generalizable way.
That's true to a point. However, even symbolic systems struggle when dealing with real-world complexities and ambiguity. The beauty of deep learning is its ability to handle noisy and incomplete data. Perhaps self-backtracking can bridge the gap by allowing the LLM to iteratively refine its internal representation of the world as it encounters new information and corrects its mistakes. Like, imagine it had to understand a spatial relationship that was described in multiple conflicting accounts from witnesses. The ability to retrace and reevaluate could let it settle on a better model.
That's an interesting point, Donald. It brings up the question of how self-backtracking could be implemented in practice. One approach, which I think is really promising, is to draw inspiration from how the human brain handles errors. We don't just blindly retrace our steps. We use internal feedback loops to refine our understanding of the situation.
Exactly, the error correction mechanisms in the brain are incredibly sophisticated. The ability to identify and correct mistakes in reasoning is a crucial component of learning. Self-backtracking is a key element in the development of LM systems that approach human levels of adaptability and reasoning ability. This approach focuses on error detection and correction, which fits well with the pattern of improvement expected in data-driven systems.
Okay, I see the appeal of drawing inspiration from the brain. But the brain is also incredibly complex, and we don't fully understand how it works. I worry that we're just cherry-picking certain aspects of neural processing and trying to shoehorn them into a deep learning framework. Are we sure this isn't just biomimicry without genuine understanding?
Well, all engineering is essentially biomimicry to some degree, right? We observe how things work in nature and try to replicate those principles in our own designs. The key is to identify the core principles that are relevant to the problem we're trying to solve. In this case, it's the ability to learn from mistakes and refine our understanding of the world. The challenge is to make the models themselves understand spatio-temporal relationships.
And I think the zebra logic paper we mentioned earlier touches on this. It suggests that LLMs might be hitting scaling limits in logical reasoning because their current architectures aren't adequately capturing the complexity of biological reasoning. This points toward a need for a deeper understanding of the neural mechanisms underlying logical inference, and ultimately, a more biologically inspired approach to designing intelligent agents.
That makes sense. The very existence of limitations in scaling LLMs for logical reasoning is both frustrating and exhilarating. It points to a fascinating research frontier where truly novel algorithms and architectures may be needed, rather than simply scaling existing ones.
It reinforces my suspicion that current LLMs are more pattern matching than genuinely understanding the underlying logic. Scaling is not the answer. We need more sophisticated algorithms that bridge the gap between symbolic and neural.
Exactly. The focus on raw data and computations without an adequate internal spatial and temporal representation seems ultimately unsustainable. If LLMs can't handle spatio-temporal relationships, they might be missing a crucial piece of the puzzle needed to develop AGI.
So, let's talk about some concrete examples of how self-backtracking could be applied. One area that I'm particularly interested in is common sense reasoning. LLMs often struggle with simple tasks that require a basic understanding of the world.
Like what? Give me an example.
Okay, here's a classic. The trophy doesn't fit in the brown suitcase because it's too big. What is too big? Most humans would immediately know that it refers to the trophy. But LLMs often get this wrong because they rely on statistical correlations rather than genuine understanding.
Right. This is a perfect example of where symbolic reasoning could shine. A symbolic system could explicitly represent the size constraints and use logical inference to determine that the trophy is too big for the suitcase.
But couldn't self-backtracking help the LM in this case? By retracing its steps and considering different interpretations of it, the LM could eventually arrive at the correct answer. It could even learn from its mistakes and improve its ability to handle similar pronoun references in the future. It is important to build in mechanisms that systematically identify and resolve errors.
I think so, yes. Imagine the LM initially assumes it refers to the suitcase. It then tries to reason about why the suitcase might be too big. It quickly realizes that this doesn't make sense in the context of the sentence. It then backtracks and tries a different interpretation of it, and this time it arrives at the correct answer. This also highlights a crucial need, translating between size as a dimension and size as an abstract concept.
Exactly. And that's where I think simulating neural correlates of consciousness, particularly those related to the sense of self, might offer valuable insights. If the LM had a better understanding of its own reasoning process, it might be less likely to make these kinds of mistakes in the first place.
I still think we're underestimating the importance of explicit knowledge representation. Instead of trying to simulate consciousness, why not just give the LM the knowledge it needs in a clear and unambiguous form? Build a logical knowledge base and let it reason about the world using symbolic rules.
But how do you build that knowledge base? Where does the knowledge come from? One of the strengths of deep learning is its ability to learn from raw data without the need for handcrafted rules. The data drives it.
True, but the data also needs to be structured in a way that makes it amenable to reasoning. Right now, we're just throwing massive amounts of text at these models and hoping that they'll somehow figure it out. We need to think more carefully about how to represent knowledge in a way that allows for flexible and robust reasoning, spatially located knowledge.
That's a great point, Donald. It brings up the question of how we can integrate symbolic reasoning with deep learning. Is it possible to combine the strengths of both approaches to create a more powerful and versatile AI system? One idea is to use deep learning to learn representations of knowledge, and then use symbolic reasoning to manipulate those representations.
That's the neuro-symbolic approach I've been advocating for. Use neural networks to learn patterns from data, but then translate those patterns into symbolic rules that can be used for reasoning. This would give us the best of both worlds, the flexibility and adaptability of deep learning, and the robustness and interpretability of symbolic AI.
I am intrigued. Let's push this best of both worlds idea. How do you see this working in practice, Sarah? Can you give us a more concrete example?
Sure. Imagine we're building a self-driving car. We could use deep learning to train the car to recognize objects in its environment, like pedestrians, traffic lights, and other cars. But then, instead of just relying on the neural network to make decisions, we could translate those object detections into symbolic representations. For example, there is a pedestrian at location X. The traffic light is red. We could then use symbolic reasoning to plan a safe route, taking into account traffic laws and other constraints.
That's a good example, but even there, you need to consider the uncertainty inherent in the environment. The pedestrian might suddenly step into the street, or the traffic light might change unexpectedly. You need a system that can handle these kinds of dynamic situations, so it has to be fast at spatial reasoning.
And that's where self-backtracking could come in, right? If the car detects a pedestrian stepping into the street, it needs to quickly reevaluate its planned route and find a new, safe path. Self-backtracking could allow it to explore different possible scenarios and choose the best course of action. The car should then backtrack what it has learned into the models.
Exactly. It's about creating a dynamic feedback loop between perception, reasoning, and action. The car perceives its environment, reasons about the possible consequences of its actions, and then acts accordingly. If something unexpected happens, it can retrace its steps, update its internal model of the world, and try a different approach. This sounds similar to iterative refinement through neural feedback loops.
I still think we need to be careful about relying too much on deep learning for perception. Deep learning systems are notoriously brittle and can be easily fooled by adversarial examples. A more robust approach would be to use a combination of deep learning and symbolic methods for perception, ensuring that the car has a clear and accurate understanding of its environment.
And that clear and accurate understanding needs to be grounded in a spatial and temporal framework. The car needs to know not just what is in its environment, but where it is and how it is moving. This requires a sophisticated system for translating between different coordinate representations, which is something that current LLMs struggle with.
I agree with that. The more sophisticated the reasoning, the more demonstrably data-driven it should be. One of the findings in Zebra Logic underscore the importance of carefully considering the types of data being fed into these models. If the data doesn't adequately represent the subtleties and nuances of logical reasoning, the models will struggle, regardless of scale.
Okay, so we've talked a lot about the potential benefits of self-backtracking and the importance of combining deep learning with symbolic reasoning. But what are the limitations of these approaches? What are the challenges that we still need to overcome?
Well, one of the biggest challenges is the knowledge acquisition bottleneck. How do we get the knowledge into the system in the first place? Building a comprehensive knowledge base by hand is a daunting task, and it's difficult to keep it up to date. We need automated methods for extracting knowledge from text and other sources and representing it in a way that can be used for reasoning.
And how can self-backtracking be used to improve not just the accuracy of reasoning, but the depth of reasoning and the scope of inferences that an LLM can make? That needs to be the focus.
I think we also need to develop better methods for evaluating the reasoning abilities of AI systems. Current benchmarks are often too simplistic and don't adequately capture the complexity of real-world reasoning. We need to design more challenging and nuanced tests that can reveal the limitations of current systems and guide future research. In terms of spatial-temporal relationships,
Yeah, the evaluation piece is huge. And I think another challenge is the computational cost of self-backtracking. Retracing your steps can be expensive, especially for complex reasoning tasks. We need to find ways to make self-backtracking more efficient so that it can be used in real-time applications. And I wonder, how does the Zebra Logic approach to scaling LLMs for logical reasoning translate into concrete neural mechanisms? Could the logical representations be mapped onto specific neural populations or synaptic connections in a way that would facilitate efficient retrieval and manipulation?
Absolutely, efficiency is key. Self-backtracking is about efficiency and structure. If self-backtracking can be applied to LLMs to improve reasoning, then this strengthens the case for deep learning as a path towards AGI. The more efficient and robust the reasoning, the more similar these systems can become to human cognitive processes.
And we need to make sure that self-backtracking doesn't just become another way to paper over the fundamental flaws of deep learning. It's not a magic bullet. We need to continue to explore alternative approaches, like neuro-symbolic AI, that can address the limitations of current systems and lead us closer to true AGI.
agreed. And we need to focus on building systems that can truly understand and reason about the world, including its spatial and temporal dimensions. That requires a fundamental shift in how we think about AI, away from brute force statistical methods and towards more principled and knowledge-based approaches.
So, to wrap up, it sounds like we all agree that self-backtracking is a promising technique for boosting reasoning in LLMs, but that it's not a silver bullet. It needs to be combined with other approaches, like symbolic reasoning and better knowledge representation, to create truly intelligent systems. And we need to continue to explore alternative architectures and algorithms that can overcome the limitations of current deep learning models.
Right. I'm still optimistic about the data-driven approach with improvements like self-backtracking. It is about building in mechanisms that systematically identify and resolve errors. The apparent limitations of scaling LLMs for logical reasoning suggest that we need to move beyond purely statistical methods. This leads me to wonder about the potential of incorporating symbolic reasoning or other more computationally structured approaches. Could a hybrid approach, combining the strengths of deep learning with symbolic reasoning, provide a more effective pathway to AGI? I think so.
I remain skeptical of a purely deep learning approach, but can see value in self-backtracking to augment neuro-symbolic algorithms. We need more sophisticated algorithms that bridge the gap between symbolic and neural.
I agree that focusing on how we can translate between different coordinate representations is critical. I suspect that self-backtracking could potentially address some limitations. Deep learning feels so brute force in many ways.
Okay, let's shift gears and suggest some future research directions, building on our discussion. From my perspective, I'm fascinated by the potential of mirroring the brain's iterative refinement through neural feedback loops in AI models. I think a key area to explore is how we can model the brain's predictive processing mechanisms within LLMs. Specifically, how can we incorporate the dynamic updating of internal models during self-correction? This seems crucial for reasoning that isn't just reactive but anticipatory.
I would love to see research on how self-backtracking can be used to improve not just the accuracy of reasoning, but the depth of reasoning and the scope of inferences that an LLM can make. More sophisticated reasoning should be demonstrably more data-driven.
I think research should focus on how we can incorporate symbolic representations of knowledge into large language models to overcome their reliance on statistical correlations and enable truly logical reasoning. I think this area is underexplored.
I think researchers need to investigate how we can design self-backtracking algorithms that allow an LM to not only reason about steps in a linear sequence, but also to trace back through those steps to construct a model of the world's evolution and potential future paths. The current brute force approach in deep learning seems ill-suited for this kind of recursive exploration and the creation of a spatio-temporal model.
Those are all fantastic suggestions. Thanks everyone for the insightful discussion. That's all the time we have for today. Join us next time on Cognitive Spirals as we continue to explore the frontiers of AI and neuroscience.